Okay, it just points out here that as far as heat and temperature are concerned, we're going to make a distinction here between heat and temperature. They're not the same thing, all right? They're different things. So to start off with, this is just a slide to point out that when you have some materials that are in the solid state, they're pretty close together. They're moving, right? But they're vibrating and all, but they're close together. And then when you heat them up, they vibrate more and they get to a point where they can slide over one another. And that's when you have a liquid. Okay, and finally, when you give them even more energy, then they can escape into the air and be completely free, okay, of each other. And that's when you have the gas state, okay? Makes sense? That's a model that's been around for a few hundred years. Let's see, can I go there? Yes. So, all atoms and molecules will contain energy, and that energy is made up of two things. It's made up of potential energy, like the energy we have between us and the sun, right? It's a gravitational potential energy. Well, molecules have that again between each other the same way. That's called your potential energy, but they also have kinetic energy because they're moving all the time. Molecules, the atoms are always vibrating or rotating. They're always moving in different ways. This movement, this kinetic energy of the molecules is what we call the temperature. It took us a long time to sort all this out. You can imagine, like a couple of hundred years. But in any case, heat is actually the total energy of the molecules altogether. Then, as it says here, heat's a form of energy. When a substance absorbs heat, its molecules increase their kinetic energy. This increase in kinetic energy can be used to increase the temperature or change its phase. So you can do two different things. When you put heat energy into something, you can either just have it warm up, or you can have it change phase, meaning from solid to liquid, or liquid to gas. All right, we'll talk about that a little bit later. There's energy associated just with that, with going through that change of phase. And these two things are different, okay? The amount of heat you need to change phase, when you change phase, you change it at one temperature. As you'll see later, your temperature doesn't change while you're changing phase. But we'll talk about that later. But I just want to introduce that to you now. Okay, so temperature tells you how hot or cold something is, and as you guys know, there are two different scales that we use today. There's the Celsius or centigrade scale and the Fahrenheit scale. The Fahrenheit scale was developed first, and it's very practical. The man that did it did a lot of work in his laboratory with salt solutions, and he said, I'm going to make 0 when my salt solution freezes, and I'm going to make 100 the temperature of everybody in the lab here. You go in, take your temperature, and he averaged all those up, and he came up with the Fahrenheit scale. But then about, I think something like between 50 and 100 years later, Andrew Celsius came up with a simpler way. He said, wait a minute. He said, this is too complicated. Everybody's temperature varies a little bit, and not everybody has the same salt solution, so the one thing everyone has is pure water. In every laboratory, they could distill water and make it very pure. So he did a similar thing. What he did is he took water and he froze it, and he called that 0, right, which is similar to what this guy did, but with a salt solution. And then he boiled the water, and at atmospheric pressure, water boils at what he calls 100 degrees C. And that's how we set that scale up. So it turns out, when you get away from the salt solution and use pure water, it freezes up here at 32, and water will boil on this scale at 212. And of course, we're probably most familiar with degrees Fahrenheit when it comes to our everyday life, but in terms of our work in hospitals and all, you probably deal with degrees C a lot more, the Celsius scale. We're the only ones in the world who still use degrees Fahrenheit. I think there's one small country that still uses Fahrenheit. One that was a British colony or a French colony many years ago. But in any case, we're the only ones. Everybody else, you go up to Canada, you go to Mexico, you go to Brazil, no, you might get pregnant. Don't go to Brazil, okay? Bad idea. But when you travel to any other country, they'll all use degrees C when you go there. So, anyhow. So those are the two scales, and there is a third scale called the Kelvin scale, named after a man who did a lot of work with heat and temperature, a Scotsman, and in the last century, actually century before last, now in the 1800s. But his name was actually Billy Thompson, but he did a lot of work with temperature, and he wrote a lot of papers and so forth, and did, a lot of work with heat. And he got made a what do they call it, a peer of the realm, or in effect like being knighted or being made a dame if you're a woman. But the thing is that the king would take a sword, and touch your shoulders and so forth, and you were now a high-ranking, a lord. All right, it would now be a lord or lady that you would be. And in any case, when you do that, you're allowed to take any name you want. And so Billy Thompson said, well, growing up in Scotland, I spent so many wonderful years as a youth swimming and fishing and ice skating on the River Kelvin. And so he said, I'm going to take the name Lord Kelvin. So that's the real story of where that came from. But anyway, the Kelvin scale is the one where we've been able to determine where what they call absolute zero is. And that's a temperature at which the molecules have, of course they still have energy, they have potential energy, but they have no kinetic energy. And we've been able to do that by cooling gases, different gases, and as you cool them, we found that as their temperature drops, their pressure drops, but they all, as they cool down, they all head toward the same place on the graph. You can't get all the way there because the gas liquefies and then the experiment's over. But as you're cooling the gases, they all pointed to the same place, and that's what we call absolute zero. Now this is important, the Kelvin scale, and I don't know why they don't call it degrees Kelvin, but they don't, they just call it Kelvin. But in any case, that's absolute zero, and this is the Kelvin scale on using the same size units for temperature as the centigrade scale. So when you do that, you can see that the Kelvin scale of 0 turns out to be minus 273 Celsius. And then as you go up and have 273 Kelvin, that's 0 over here and so forth. You guys see that? It's just, this is the equation here. The temperature in Kelvin is going to be the temperature in degrees C plus 273. Okay? So far? You need the Kelvin scale, it turns out, for any gas calculations that are made. If you use any gases and want to make calculations about pressures and temperatures and so forth of the gases, you have to use, when you use the ideal gas, what do they call it? Well, any of the gas laws, like Boyle's law or Charles' law and so forth, you have to use Kelvin instead, or else you get the wrong answer. It can't be, even though this is the same size degree in C as it is in K, you have to use these numbers in order for those equations to work. Okay, now, on this one, all matter contains energy. We talked about that already. So if you put two objects that have different amounts of kinetic energy in contact with each other, then what passes from one to the other is that energy, that kinetic energy, and we call it heat, is that energy, that kinetic energy in transit, all right, going from one to the other. Now, I don't want you to think that it stops when you get the same temperature. The kinetic energy is still moving through both of the bodies at the same time. It's moving through both of these objects. But the point is that they're all at the same temperature. So, but in theory, they're still moving in both directions. But you guys know this, of course. You take something warm and you put, you put it next to something cool, and you know that they're going to reach an equilibrium temperature at some point. Okay, but that's the reason. It's because the kinetic energy is being moved from one to the other. Okay, so heat flows, this kinetic energy moves in response to temperature differences, and heat is the net movement of the average molecular kinetic energy. And there's actually a formula for that, but but we're not going to go into that. But the thing is, the heat always flows from the higher temperature to the lower. Now that was hard to figure out in the beginning, because when you have two objects, a cool one and a warm one, and you put them together, and they come to one temperature, right? But did the hot go to the cold, or did the cold go to the hot? When you think about it, it could work either way, all right? But it took a while for scientists to figure out that heat was related to kinetic energy, and then that's what allowed them to make that statement. So a thermometer, when you put a thermometer in contact with this substance, what does it do? It absorbs that heat from the substance so it becomes the same temperature as wherever you place the thermometer. And then once it gets in equilibrium with that, with the kinetic energy, then it stops, okay? And that's the temperature that you read. We okay so far? Are we making sense? Good. Now, okay, whenever an object takes in or gives off heat, the internal energy changes. Now, reading this and using your book, I think your book uses both units for heat. We've talked about energy as being in joules, and that's what the unit for energy is in the International System of Units, is joules. But another unit that's been around for a long time is the calorie. Okay, and so you will see problems sometimes where they're talking in terms of the amount of heat you have in terms of joules, or they may talk about it in terms of calories. But I want you just to realize there's just a simple conversion from one to the other. Okay, roughly 1 calorie is about 4 joules. That's it. So if you see, I don't want you to be concerned if you see a problem with a joule and a calorie. Because just stay with that unit, whatever it is. When we do the lab, we'll be doing the lab in calories. Okay, the numbers are smaller, they're easier to work with. But your book has some problems that I think will be in joules, so you have to just remember that I want you to be able just to switch from one to another. But just remember, whatever the problem is dealing with, whatever energy unit they're giving you, stay with that unit. Okay? You probably have a table in here where they give you different values of temperature, and I just want to see if they give you both the joules and the calories. Yeah, because see, yeah, okay, well, I'll wait till we get to that. There's just, it doesn't seem, they don't seem to be as much of a problem with your book as some other books, other physics books. Okay, but there are those 2 units. And by the way, the calorie that you'll see written is with a lowercase c, all right? When you see it with an uppercase c, it means a kilocalorie, 1,000. So whenever you look at the label on, in a bottle or a soda or food, all right, it will always be spelled with a capital C. It means a kilocalorie, or 1,000. Doesn't make you feel so see. Eat that candy bar. If you think it's 200 calories, no, it's 200,000 calories, right? If you go to the real calorie unit. But so anyhow, okay, that's why there's always a capital C there. It means a kilocalorie. Now, the amount of heat that you need to raise the temperature of something depends upon the mass. That only makes sense. Right? If you want to heat up 2 different volumes of, let's say, of water, obviously, given the same amount of heat, the lesser mass is the one that will heat up more quickly, right? This only makes sense. So, but one of the problems with this is scientists just thought, well, that's easy. We can always figure out how much heat we need to raise the temperature of something by just figuring out how much mass there is. Boom. No, wrong. Because there's another characteristic that all substances have called, they gave it a name because they're not very clever, but they just called it specific heat because it's something that's specific to that particular substance. For example, let's say you go to the beach in the summer, okay, you get down on the sand, you take your sandals off, you step on the sand is hot, right? Okay. But you go in the water, and the water is pretty cool, right? Maybe the water is in the summer, maybe it's 80 degrees, okay? It's nice temperature, all right? Now, but you come back, you go have dinner, you have, you have a few drinks, and now you want to go back and take a nighttime skinny dip, so you go down to the beach, and when you take your sandals off at nighttime and put your feet on the sand is cool, isn't it, right? But you go in the water will be the same temperature it was during the day. Okay, virtually the same temperature. Why is that? Right? That's because of this thing called specific heat. All right, water is of all the substances out there. Water is a substance that changes its temperature very little with heat that's added to it. That's why it takes water so long to boil. All right? You got to put so damn much heat in it to get it to boil. On the other hand, substances like the sand pick up the heat from the sun right away. They change their temperature quickly. The sand does. And then when the sun disappears, they lose the heat quickly. But the water stays right about the same temperature. This is just an example I like to give of specific heat. Or another example might be, before I came here tonight, I had some pizza, okay? Now, when you go to the restaurant, you order pizza, all right, and they bring it out, it's hot, so ooh, I let it cool for a minute, right? So you let it cool, all right, and then you get to a point where you can pick it up, or pick up the piece of pizza, and you bite into it, and you burn the top of your mouth. Doesn't that happen? All right. Why is that? You just picked it up with your hands. You know it's not going to burn you. What burned the top of your mouth?
The cheese.
The cheese. And what else is on the pizza? Sauce, right? And what do cheese and sauce contain? Water, right. So that water holds that heat, right? It's ready there to burn the roof of your mouth. Whereas the crust is more like the sand, and that picks up the heat quickly and then gives it off quickly. But that's an example of what's called the specific heat capacity, or we shorten and just say the specific heat. And that's what we'll be measuring for a piece of metal in the lab. Oh, here, as a matter of fact, I had an example of it here, but so I'm glad I asked you first. But anyways, the crust has that lower specific heat value, which means it heats up right away, like, say, a frying pan. You put that on the stove, turn the stove on, heats right up, okay? But on the other hand, I'll give you an example. You might want to even try this. No, don't try this entirely at home. If you take a frying pan, put it on the stove, crank the stove up to high, and wait about 1 minute, and then put your hand in the frying pan. What's going to happen? Burned, right? Okay, now, go back to start the experiment over. All right, you have a room temperature pan. Put it on the stove, except this time, put about a centimeter, maybe a half an inch of water in the pan. Now crank up the heat, wait that minute, take your hand, put it in the water. No problem. Okay? It's another example. I just want you to see how water is so unique in that it can hold so much heat energy without changing its temperature. Whereas something like, the aluminum or the copper or the steel pan, whatever you've got there, low specific heat picks up the changes, it heats up quickly, cools down quickly, just like the sand does, or that's why deserts are so hot during the day, but then they get very cold at night. Okay? You need a park on it at night, some deserts. Okay. Now here's an example of some things like water. They assigned water a specific heat number of 1, and that's what we use in the calorie system, not the joule system. So it's in calories per gram or kilocalories per kilogram. It's the same thing. Water is 1. The aluminum, for example, is 0.2. Steel is about 0.1. Sand is about 0.3. I just want to point out here that with this, you can see here it takes about 4 times as much heat energy to warm up water than it does aluminum, because aluminum heats up so quickly. You'll need a lot more heat energy in order to heat up the water to the same temperature. Did I give it? Yeah, I gave an example of this too. Many, many years ago, I had an aunt that when she was a young lady and got married, she bought, or maybe she was given as a gift, kitchenware, cookware. And in her day, which was like in the 1930s maybe, in her day, pots and pans that were really good quality were made of aluminum. Okay, and so she had a nice aluminum, like a sauce pot. She would make tomato sauce, or she would make soup and so forth in it. But it was all aluminum. That's what the cookware was like back in those days. But today, because we know about specific heat, now we make them differently. We say, oh yeah, you want the bottom to be aluminum or copper, or even better, it's gold and silver, but who can afford that? But the thing is, for aluminum on the bottom, you want the heat to go right through into the pan, whatever's inside that pan. But to protect the heat from escaping, they put stainless steel around the outside and on the lid, which the heat still escapes, of course, but slower, much slower, only about half the rate that it would from the aluminum. So whenever I make sauce, I think of her and I make soup or something and use that, you know, I know I'm losing a lot of that heat into the room when I do it. But in this case, I'm trapping more of it inside that saucepan or that cooking pot, okay, because the steel is not allowing it to escape as quickly, okay? Steel has a higher, the steel that they use. That's why when you go into, what is it, like any kind of a cookware store, and you look at Williams-Sonoma especially, yeah. When you're going to look at the cookware there, you're going to see all different kinds of metals, you know, welded together. But this is one of the things that they do to help you contain as much heat as you can in whatever you've got in that cooking pot. Okay, that's one of the things that they've done. So engineering, in other words, has come more into the kitchenware area. Okay, we already talked about this, but about the beach and how the whether it's daytime or a nighttime, the difference in the sand temperature as opposed to the water temperature. We already talked about that. Here's the formula. Ta-da! Okay, it says that the heat that you need, if you want to raise the temperature of something, let's say you want to take the temperature from room temperature, which is, we use degrees C here now, so let's say you want to take it from 22 degrees to 50 degrees, then you would this would be the difference in temperature. So here you would have 50 minus 22, okay? How much heat do you need? Well, you need to figure out not only how much you want to change the temperature, how much mass are you going to be heating up? And what is the specific heat capacity from a chart? What is the value for that substance? All right, so this is how you would do that. That's the amount of heat you need, and it works in the opposite direction too. If you using the same mass and the same specific heat for the same substance, if you went from say 50 degrees down to 22 degrees, this would just come out to be a negative here, and it would just mean that's the amount of heat that you got back, okay, from it when it cooled. All right, so the formula works in both directions, whether you're heating up or cooling down. Okay, and I just put the units down here, calories, and then the mass is in grams. This is what we use tomorrow night and Thursday night, is in grams. This is in calories per gram here, and then this is just in the degrees C, the temperature change. Okay, so this was an example. How much heat do you need to heat up 100 grams of water to 100 degrees C compared to 100 grams of aluminum to 100 degrees C? And this is where I just wanted to show you how that specific heat can make a big difference. In the case of the water, it's going to take, you have 100 grams, the specific heat of water is 1, you're changing its temperature from 20 to 100, so it's going to take about 8,000 calories. But for aluminum, which has a specific heat of only 0.22, even though it's the same mass and the same temperature change, look at how much less you need, how much less heat. This is why the aluminum heats up so quickly. So remember, lower specific heat, the faster that substance will heat up and cool down in both directions. Okay? This is a long night. I'm sorry, guys. This is a long chapter. Okay. All right. If you guys want to take a break at any time, let me know. Okay, but we're what? Are we about halfway through? Yeah. All right. Okay. Now, expansion. Most, because I won't go into any more detail on the heat stuff until we'll do the lab, and we'll talk more about calorimetry then. And in the case of calorimetry, the lab, what we're going to do, I'll just tell you, but you're going to take a small amount of water, okay, in a little container called a calorimeter, because it's insulated in a little container. We're going to take water at about room temperature, and we're going to take a piece of metal that you're going to heat up to 100 degrees C by dipping it in boiling water, all right, for a minute or two. Then you'll take that metal out and put it in the small amount of room temperature water here. And of course, you know what's going to happen is the heat is going to come out of the metal, go into the water, and raise the temperature of the water by a few degrees. Okay, and when it does that, all you have to do is measure how much did it change the water temperature, and you can go back and what we'll do in the lab is you'll be able to figure out what the specific heat is of that metal object that was in there. But, okay, now we'll move on to this. When you heat up objects, okay, substances, they expand when they're heated and they contract when they cool. You may have noticed if you go over bridges, when I used to ride a motorcycle, I would always notice these, maybe you guys, I don't know if you always notice them in your car as you go over a bridge, you probably just go over it. But on the ends of the bridges, you know, like if you go over the Sanibel Causeway, for example, you know, or go to Cape Coral, you'll see that there are, on each end, there are, as you're going forward, you have these metal fingers that are stuck together. That's a better drawing than my hands look here. But the point is that they are there so that in the summer, when the concrete and the steel and so forth expand because they've gotten warmer, these teeth can get closer together. Okay, and then in the winter, when the concrete and steel shrink, all right, they have room to move apart. Okay, this is really important stuff. People become architects have to get really knowledgeable about this when they're building, when they're making designs of buildings. You know, how are the walls going to move? How's the glass going to move? And you know, and all the structural components. This is very important to be able to accommodate the changes in temperature. In any case, you may see these when you go over the bridge the next time. If you notice it, you'll say, "Oh, I know what that is. That's to allow for linear expansion of the bridge and contraction." So, another thing that's very common in use, it has been for, gosh, probably a century, is what's called the bimetallic strip. Right? It has nothing to do with babes. All right. This is a. What you've done is you take two pieces of metal, like two little sheets of metal, and you weld them together, all right, and they're different metals. And because they're different metals, they will expand and contract at different rates. So what I was trying to show you here is that at room temperature, you might have it nice and straight, nice and flat. But when you cool it down, one of them will contract more than the other one. And that will cause it, if you hold this end fixed, that will cause one end to move up. Okay, and then if you heat it, then this same one will expand more, and as a result, it will bend down the other way. They use these in thermostats, and I don't know if I put the one in here about, yeah, I did, your directional signal in your car. Did you ever wonder what that little click is that you're hearing in your car? It's when you turn the directional signal on, there's a switch there that normally the switch, the little bimetallic strip is in contact with this other leg of the circuit. So when you first put the directional signal on, current flows through the wires and turns your light on, all right, to tell the other people you're going to make a turn, okay? But what happens is, in a matter of usually like a second or so, that little bimetallic strip heats up and pulls away from that other contact point. So the way I have it there, it would just sort of pull away like this. All right, now that opens the circuit, so the light goes out. No current can flow. Okay. But then the strip cools down and comes up in contact again. Now electricity flows to the light bulb, but then when the strip heats up, pulls away. That's that little click that you're hearing when you turn that on. See all these practical things you learn in this class. These things you just always wanted to know, right? Anyway, that's another use for a bimetallic strip. In addition to thermostats in the house. But anyhow. Now, water, one unusual characteristic of water is that, like all other substances, when you cool water down, it contracts. However, the unusual thing about water, the thing that's not usual at all, is that when you just get down to about 4 degrees C, when you get down to 4 degrees C, the water stops contracting and it starts to expand. Okay? So this is very unusual, but this is the reason that ice floats, because ice is less dense than the water that it's sitting in. So this is why if you have the air out here, for example, over a lake can be very cold, say like minus 20 degrees, but here in the water, because of this layer of ice here, the water underneath the ice will never change temperature anymore. So if you're ever asked, what was the temperature in Lake Michigan on January 18th of 1956? You know, you can always say and always be right, 4 degrees C. That's as cold as it gets in the water. It won't get any colder than that. You don't believe me? Let me give you an example. Oh, I need an eraser though. Oh, here's one. Okay. Here we are. Here's the lake. Well, that doesn't work very well. How about this? That's better. Here's the lake, all right? So this is all water down here, all right? So let's say the air temperature is 6 degrees out here, all right? 6 degrees, and the water is, say, 6 degrees. Now, the temperature outside drops, and now it's 5 degrees. Where's my, here we are. The temperature out here drops to 5 degrees. All right, the wind is blowing. What happens? The water on the top gets to be 5 degrees, which makes it more dense than the water underneath it, right? The water is contracting. So what happens is this 5-degree water sinks to the bottom, 6-degree water goes to the top, it gets cooled to 5. So what happens is this eventually all gets to be 5 degrees. Okay, and this goes on all the time. Then, now we get down to 4 degrees. So we get to 4 degrees on the top, and at 4 degrees, the water gets, it's most dense, it settles back down, settles down to the bottom, and the warmer water at 5 degrees goes up to the top, and you get the same circulation of water until all the water is 4 degrees. Okay. Then, if the outside temperature drops more, and let's say goes to 3 degrees, what happens now is the water on the surface doesn't get more dense, it gets less dense. So it doesn't sink, it just stays right where it is. So you end up with a layer of ice here, and underneath it, that water, I don't care what this is, it can be minus 13 degrees, doesn't matter. This is at 4 degrees underneath. And those little fishes are very happy down there on the bottom. But that's true, that's because water becomes less dense when it forms a solid. I don't know if I have a slide of that or not. No, I didn't. But what happens to the water molecules are, as you cool them down, they get closer and closer together until you get to 4 degrees. That's as close together as they get. After that, they begin to separate. And what they do is water forms, when it freezes, it forms a hexagon. That's why snowflakes are all shaped in the hexagon shape. This is how, and this is oxygen, here with hydrogens linking them together. But the point is, in the middle of the water molecule hexagon is empty space. So that's what makes this less dense than the liquid water that's right nearby, which is where they're all close together. Okay, and that's why ice floats. That's very unusual. Nothing else has that characteristic. Okay, what's next? How do we transfer heat from one place to another? There are 3 different ways it's done. It's with radiation, convection, or conduction. And I just give a quick example here. The thing is, conduction is if you take a spoon and you put it in, say, some hot coffee or hot soup or hot tea or something, I think you'll know that, especially if it's silver spoon, all right, the handle quickly gets warm, okay? That's because the heat energy is traveling up the spoon. No mass is being moved. It's just the heat energy itself. When you iron a blouse, you iron a pair of slacks, okay? The iron isn't going into the slacks. So what's happening is the heat, only the heat energy, the thermal energy is what's being transferred from the iron to the clothing, okay? No movement of mass, no molecules, just the energy, okay? That's conduction. Convection, on the other hand, is where you now are going to change the temperature of something and then physically move it. This is how furnaces work and how air conditioning works. All right? If you need air conditioning, what does your unit do? It cools the air in one area, it gets it nice and cold. In your car, it's less than 60 degrees. It's like, I think when they check your car, it's like 54, 55 degrees coming out when it's working at 100%. And what happens is you get that cold air, but then you move it somewhere. So, in your case, you might say get that nice cool air in the summer in your air conditioner, and then the conduits and fans take that cool air and drop it into your kitchen or your bedroom or your TV room or whatever. You know what I mean? But here, you're not only moving the heat energy, you're moving mass at the same time. Okay, do you see the difference between convection? Or a convection oven is one where, what do? You're moving the air in the oven all around to create a uniform temperature in the oven instead of having it be the normal stratified temperature. You need different shelves for things. So, by the way, oven temperatures are usually wrong. I don't know if I was reading a book recently where they studied, one of the things the guy studied was he had chefs who bought new ovens with a really good temperature gauge, check the temperature of the ovens. And he said, set it for 350, and what does it read? And it turns out they were all off like 5 to 15 degrees one way or the other. They were all wrong. So anyway, so in case you screw something up when you're baking it, you have an excuse there. Say the oven's not quite right, which is true. Anyway, the last way is radiation, and that's what you feel when you get near a campfire or near a fireplace. You can feel that heat radiating from it. That is radiation. That's infrared radiation coming directly through the air and actually through space. So, let's see. I put point down here about this is the greenhouse effect also, but the greenhouse effect is really the same thing that happens to your car when you leave your car out during the day with the windows all up. Okay, when you get in it later on a day like this, you like it to be nice and warm when you get in there, right? But the sun does that because the energy, the light from the sun, comes through the windows and hits things in the car, and when it gets reflected from your seats and the dashboard and all, it loses a little energy, and that little bit lower energy creates a little more infrared radiation, and that can't get through the window. So that's what gets stuck in your car, that infrared energy. And that's how the greenhouse effect works, okay, in true greenhouses. The greenhouse effect for the air is different. That's because the infrared radiation that's coming from the Earth can't get out, but not because of glass, but because of the things like carbon dioxide and water molecules in the air absorb that infrared radiation and re-radiate it. And so you can imagine if from the Earth you have this infrared radiation heading out towards space, and then it hits some of these molecules, they absorb it, but when they re-radiate it, they'll re-radiate some of it towards space, but they'll re-radiate some of it back toward the Earth in different directions. And that's what tends to trap the heat here. So it's not exactly the same as what we have with glass, but anyhow, there is a little difference, although the net result is the same. You're trapping heat energy. Oh, well here, this is just more detail. I forgot I had this on here. But you guys know this time of year, it's nicer to walk on carpet than it is to walk on that tile floor, right, with your bare feet, okay, because the tile floor is cooler. Why? Because it's, well, look this way. You do that, right? You put your hand on the desk or a table, you say, it's cool. No. It's at a lower temperature, and it's sucking the heat out of your hand, okay? And our brains are already wired, since we're little kids, to say, oh, that sensation means cool, okay? And of course, hot is just the opposite. When you touch something and it's hotter. Now it's transferring the heat into your hand, so it's... But in this case, the tile floor is something that just quickly will take heat out of the bottom of your feet. Whereas if you have a carpet, the carpet is there because the carpet is helpful because it's a poor conductor. It has a lot of trapped air in the fibers. Or maybe any of you have like a down comforter. Anybody ever used one of those? A little down comforter? My wife bought one and somewhere she got it through the mail, and I'm telling you, that comforter is not even a half an inch thick, okay? But it's got feathers or something in it, and I'm telling you, put that on at night, and you feel like you only have a sheet on you. It's so light, and yet it keeps you warm. You drop that temperature in the house to 65 if you want. You're going to be toasty underneath that. But the reason is the air that's trapped by the feathers or whatever else they used to be in the old days, feathers, but whatever substance they have in there has a lot of air spaces that trap the air, and heat is conducted by convection and conduction through the air is very slow, and so that's how insulators work. But that's why the carpets feel a lot warmer. Let's see. Convection, we already talked about this. How the furnace works, that's a convection. Or on the stove, warmer, as it says there, warmer air warmer, when you heat up water in a pot, when it's cooking, the warmer water rises to the top, just the opposite of what we're talking about here. The warmer, less dense water rises to the top, the cooler water comes underneath, and that circulation is then what allows the water to come to an even temperature. Or during the day, you can see lots of, down here, mostly vultures or osprey, but you see these birds up in the air, and they're just gliding along without even flapping their wings. Well, that's because when they first took off from the ground, they had to flap their wings, but they're real smart about convection. They get their little bodies over a road or over an area that has a lot of greenery in it, some area that's warming up the air, the sunlight, and it's creating an upward convection current. That's why they call it a thermal. And so the bird gets itself into that thermal, and then it can get as high as it wants to go, and then it can go out and search to see look for food, or do a little hunting and gliding down. And when it's getting pretty low, it'll come over again to where it picks up a thermal and goes back up again. And that's why those big birds don't need a lot of energy to flap their wings, because they're perfect gliders. Let's see. We already talked about the greenhouse effect, so I don't have to do that again. I just had it out of sync here. But we talked about it, how your car, it is a greenhouse effect. But here, in terms of the atmosphere, while the net result is the same, you're trapping heat. It's not by glass. It's just by the re-radiation of the oxygen and the carbon dioxide molecules. And that's it. Oh, Newton's law of cooling. I just wanted to mention that to you because that's something, when I first went to college, I was studying physics, I thought I was learning a lot of things. And I remember we were having a 4th of July party. And I was like a freshman in college or something. And we got in some, I don't know, it was beer or soda or whatever it was, but it was room temperature. And my brother-in-law, he said, well, we'll put it inside in here in the freezer. I said, the freezer? What are you doing now? Put it in the refrigerator. You're liable to freeze it. And I said, besides, it gets cold at the same rate. He said to me, college boy, it doesn't get cold at the same rate. It gets cold faster in the freezer. I said, are you kidding me? And he said, no. He said, just you go look it up. He was right. Isaac Newton first figured that out. He called it Newton's law of cooling, as a matter of fact. The speed with which something cools, it depends on the temperature difference between the two. Yes, sir?
Why is it that if you're throwing out fish, you do it in cold water and not hot water? I don't understand that.
I think, let me see, I'm thinking of a couple of reasons. One of them is the cooler water will allow the fish to thaw out more slowly, okay, number one. And in the warmer water, it will, especially if the fish is going to sit around a little bit afterwards, you're going to allow bacteria to grow on the outside. That's why you may read somewhere, like chefs don't like to thaw things out at room temperature. They don't take them out and put them on the counter. They take them out the day before and put them in the refrigerator to let them cool more slowly so the bacteria don't grow on them. That
makes sense.
Okay. And is that it? Oh, we didn't do change of phase. Oh, all right. Sorry, I thought we were done. All right, sorry, guys. All right, changing from one physical state to another. Now, remember, this is not a chemical change. Okay, this is strictly a physical change. All right, water, whether it's ice or whether it's liquid or whether it's steam, it's still the same water molecule. No difference. All right, so there's no chemistry going on here. This is strictly a physical change when you go, but it does require some energy to do that. And well, let me see. That's all I'm going to say about it. Oh, that's no fair. Okay, well, the point is here, I want you to realize that when you're warming up, say you have some ice and you're warming it up. The ice warms up, first of all, to 0, right, to the melting point, okay, or the freezing point, however you want to look at it. In this case, it's the melting point. And when it gets to 0, those molecules that are like this, all right, now go like this. They clump together because now it's thawing. When they do that, they are giving off energy. All right. No, sorry, I got it backwards. You have to. Wait a minute. Let me think for a second. When you actually are thawing it, when you're going from ice to water, what's happening is you have something that's called the latent heat of fusion. Is the number. But what happens is the ice will now at that same temperature of 0, okay? You have those molecules all linked up. You now have to break those bonds, okay? So this will now take energy. So you will actually have to use heat in order to break this apart. You'll need heat energy to break these so that it goes to this. But you have to supply the energy. So I want you to realize that, I think I have a graph later about this, but, or your book, I think your book has a graph of this in here, just so you know what I'm trying to get at here. Yeah, your book has it on page 113. What happens is you have to now supply energy to break these linkages between the molecules. Whether it looks like this or whether it looks like a little box, you know, it doesn't matter. The point is you have to give enough energy so those molecules can separate from each other and begin to move around one another. And that energy is given and it takes place at one temperature, whatever the melting temperature of that substance is. So you will be supplying heat to warm up the ice, then you'll be supplying heat just to convert the solid water to the liquid water. All right, and so they'll take some heat to do that. Now, once it's all water, now what will happen is you'll just heat it and it'll just warm right up. Using the same formula that we had a few slides back, all right, where the amount of heat is the mass times the specific heat times the change in temperature. And then when you get to the point where it's going to boil, once the water reaches the boiling point at a given atmospheric pressure, because that can change your boiling point, but at sea level, what happens is once you reach that temperature of 100 degrees C, it won't get any hotter. All the energy that you're putting into that water when it's boiling is allowing the water molecules to escape into the air. That's all. So which is what we call boiling away, right? The water, you boil off the water. But what's happening is the temperature is not changing. It's staying at 100 degrees. Okay? And these are called latent heats because they're sort of hidden. You know, they're hidden. This is a latent heat of fusion, a latent heat of vaporization, it's called. But I did want you to realize during a change in phase, there is, you do have to have energy transferred, but the energy transfer does not change the temperature. All right? And that's what that little graph in your book is like. It's figure 5.5 on page 113. That's what they're showing you with the horizontal lines that are on that graph. Okay. Evaporation and cooling. These are two things that are actually they're closely related to each other. The evaporation, like whether it's from your skin, from sweat coming from your skin, or evaporating from water that's been, say, spilled on the top of a table. The point here is that the water molecules are moving at all different speeds inside that droplet, but at some point, some of them that are moving very fast and moving out will escape, okay? And that means they're evaporating, they're actually leaving. It's only the very faster ones that can do that. And the ones that are left behind, they quickly rearrange into, because you know, their temperature is what creates the average kinetic energy in here, but that's the average kinetic energy. Some are moving fast, some are moving slow, some aren't moving at all. But it's always changing from one because they're banging into one another. But the faster ones are the ones that are escaping. This is why sweating is important, because when you sweat, what happens is, let's see, I don't have that graph here, but let me just show you, I should probably show you what that graph looks like. If we look at this graph, it has here temperature, and it has here heat. I'll just say heat added. So if we start, and let's say this was 0, and use water. If this is 0 degrees, and this is 100 degrees, all right, going across this graph, what will happen is, if you say get some ice at, say, minus 20 degrees C, what you'll have to do is you'll warm the ice up to 0, and that will be that same formula that we had earlier that just says that the amount of heat you need to do that is the mass times the specific heat, in this case of the ice, times the change in temperature. You'll be using that much of this heat energy to do that. Okay, the heating that you're putting in. Then, once you get to 0, the ice has to melt, and it does that at 0. So for some time, the ice is short amount of time, the ice stays at 0, but it changes to water. It liquefies. That's that latent heat that's just due to the change in phase. Now that it's water, now it'll just go up using the same formula, except now instead of the specific heat of ice, it's specific heat of water, but now it'll go up to 100 degrees. Okay, so this is just this MC delta T here. When you get to 100 degrees though, now the next step is a change of phase. You have to go to a gas. And to do that takes a lot more energy than we had down here. It'd be a real long line up here to change it all to steam. And then of course you would then use the same formula for the steam. This is how autoclaves work. For example, they increase the pressure, so they're like a pressure cooker. You can take it up to, what do we use, like 130 degrees C or something like that, but to autoclave instruments, for example. All right, but you'll be heating up the steam down here. But anyhow, the point I want to make to you is this is the creating steam. Now, this is how sweating works. Because your body sweat, right? We put water on the outside of our skin. Now, you could get rid of that water by wiping it off. Okay. But if you didn't, if you just left the sweat there, what's happening is those faster moving molecules are leaving. And when they leave, they don't leave with this energy, which is what you have at 100 degrees, water that's on your skin. They're leaving with this energy. All of this heat energy is what they're taking. And that's why sweating cools you better than just wiping off that water, but allowing yourself to sweat. It takes that heat away from you. Or you might have heard people say, a steam burn is worse than a hot water burn. Okay, you might have heard people say that, and that what they're saying, they don't have to know any physics for that. That's what they're telling you is if you start with hot water, you're starting right here at 100 degrees hot water. Okay, come take it down to your body temperature here. You get burned. But if you're starting with steam at 100 degrees, you're starting over here. So that means, first of all, your body, your skin has to condense the steam to get hot water at 100, then burn you down to body temperature. So it's that extra energy that creates the worst burn, okay? Your body has to absorb that. So that's what that expression means. What else? We have condensation. As I said there, it's the opposite of evaporation. And how does that work? You take a cool drink and you sit it out on the counter, and after a few minutes you have all these little tiny droplets right around the outside. That's because there's humidity in the air. The water molecules, they're happy, they're running around with a lot of energy, but then as soon as they hit that cold surface, wham! All right? That just sucked that heat energy right out of them, and they're stuck there forever. Okay? But they have now just warmed up your drink a little bit with that little bit of energy. And of course, as more and more of them impact the container, what they're doing is they're warming up the container, the drink, and the container, of course. But they're warming it up because they're giving up that little bit of this energy right here. Okay, they're going from, it's not at 100 degrees, it's down here, but the point is you have a higher energy, a kinetic energy, because of its being a vapor as opposed to a liquid. So that's what that kinetic energy is, what's given up. And, oh, there is the curve, after all. Okay, the one that I've already drawn here, but I put the numbers on this one. And this would be as if you took some ice and put it in a pan, put it on the stove, set the stove, turn it on to some temperature and leave it there so the heat going in is uniform or constant, and this is what it would look like, just like what I have over here. So the ice goes up, then it goes, the latent heat of fusion allowed, that's the number, it's about 80 calories per gram here to do that. And then once you get water, then you just heat the water up to where it's steam, and then you can see this should be a lot bigger. If that's 80, this should be way out here somewhere, but that's the latent heat of vaporization. And the formula for that is just the amount of heat that you need is just look up this number for latent heat in the table and multiply it by how much mass you have. That's all. This is a simpler formula here. And I guess that's all. Well, this is from physics. This is from the high school physics class. So forget that. And, oh, there's another thing, relative humidity. This hopefully will be the end, all right? Relative humidity, all that means is it's relative in the sense that there are tables that can tell you how much water vapor, let's say a cubic meter of air can hold. How much water vapor can that hold at a given temperature? And it turns out the warmer the temperature, the more water vapor it can hold. So the relative humidity just says, well, how much real water vapor is there in the air compared to what the air could hold at that temperature? And this is why, like in the summer, you may notice you get up in the morning and the humidity outside is close to 100%, okay, of the water vapor in the air. But it doesn't rain. Let's say you go through the day without any rain. If you look at the relative humidity after lunch, you're going to see it's down around 40 or 50%. You're going to say, well, wait a minute, where'd the water go? The water didn't go anywhere. It's just that the air is warmer, and so it can hold a lot more water vapor. And so that's why we say that the percentage full that the air is a lot smaller, and that's why we say it's only 40%. That's why I was just giving you an example of that here. But it's always the actual amount of water vapor in the air divided by the how much the air could hold. The book probably has a table of this anyway somewhere. I wouldn't be surprised. Your saturation density of water vapor in the air. And it's just showing you there, and this is on page 115, but it just shows you as the temperature gets warmer and warmer, the air can hold more and more water vapor. And so on a relative basis, the way we measure it is we measure it as relative humidity, like this. So, and so, is that going to be it? Yay! Okay. Now this is, that's not your book, is it? 120? Yeah, if you just look it over. It's just about heat transfer and heat in the human body. Okay, to talk a little bit about that. But we're not going to do any math. Okay, I see there's a lot of math in here. Just for those few pages, if you would just look that over. I'm not going to test you on it.